Hello, and welcome to our Introduction to 2D Analysis webinar. This is the second installment of the DR Vision Voxel series webinar series, where we will be looking at a practical approach to beginning 2D image analysis. We're aiming this at entry-level or perhaps intermediate scientists who want to take this practical approach to expanding their image analysis skill set. My name is Willie. I handle the technical and application support here at DR Vision, and I'm going to be your host today. We're going to take a look at some real fluorescence microscopy data, and we'll take a look at some of the challenges and approaches to analyzing this data. If you'd like to follow along, I'm using our very own software called Aivia. You can download a 14-day free trial from our website at www.drvtechnologies.com. So, we're going to start off with a little bit about our company, what we do, why we're here, and then we'll get into a cell counting recipe and all of the various parameters associated with it. We'll give you a quick demo of how to use that, and then move on to cell tracking, both the recipe and all of its parameters as well. Give you another demo on how to use that, and then we'll just wrap this up. So, throughout this process, you might have questions. There's a plethora of ways that you can reach us. Let me adjust this real quickly. You can reach us at Twitter at drvisiontech, on LinkedIn, at our website, www.drvtechnologies.com, which has a brand new forum as well. I also have our marketing and sales manager, Quinn, here with me. She's moderating the chat, so if you want to post in there, feel free. All of your questions will be relayed to me, and I'll make sure that we can answer them to the best of our abilities. So let's dig in. I want to give a really big thank you to everybody who's worked on the Aivia 5 product. Twan manages our software team with Bryce, Graf, John Stansberry, Casey McBride, and Michael Shea. Chi and his group, Hideki, CN, and Mike, run our algorithm and machine learning aspects that you can see demonstrated in some of the other videos on our YouTube channel. And lastly, of course, our marketing and sales team, me, Quinn Tran, who's with me moderating the chat, Hoyan Lai, our product manager, and Luciano Lucas, our VP of marketing and sales. These are just a few of the people who've worked at DR Vision Technologies. Our group of people has been together for over 25 years now, enabling scientific advancement and improving healthcare. The executive group started in the late 80s as Neopath, where they developed an automated pap smear device. It's the only FDA-approved device of its kind, and you can see it here. It's still in use today. After that company was sold, the founders re-established a new company called S-Vision, which mostly focused on industrial applications, such as metrology. In 2008, we rebranded with a little bit of investment from Nikon. Now we're DR Vision Technologies. We have worked on a wide range of applications. The ones on the screen here are just a few of them. Everything from industrial applications like X-ray inspection and semiconductor wafer inspection to biological applications like cell detection and tracking that we'll talk about today, and more complex stuff like 3D spine analysis. We like to collaborate. These are some of our collaborators that come from all over the world, mostly focused in the US and Japan right now. We've been very successful collaborating and gaining government grants. You can see just some of the many applications that we have worked on. It really helps us to push forward other researchers and collaborators' agendas, give them better scientific results faster and more accurately. Our specialty in this process is developing software for them, while our collaborators tend to provide things like the biological image data. Throughout this process, we've developed a number of really great core technologies and competencies. You can see we've got a bunch of different patents. Most of these are in the areas of machine learning and machine learning workflows. You can check out some of our other videos that talk about this. So just to rehash, we're DR Vision. We recently launched this image analysis as a service product where we have the best-in-class software, high-end hardware, a dedicated development group, and of course the best image analysis team you can get. It's a scalable and cost-efficient process for any of your image analysis needs. Of course, the software that I'm also going to be demonstrating today is our own software called Aivia. It's got everything. It's awesome. It's got 2D, 3D, VR, time-lapse, machine learning applications, as well as 15 different recipes for all sorts of image analysis applications, and some really powerful manual editing tools that you will demonstrate in a later edition of this Voxel webinar series. And of course, what we've talked about a little bit already is our contract software development. We do everything from life sciences to metrology and quality control. So let's start to talk about what you're all interested in. Cell counting, beginning analysis. If you tuned in last time, you're probably already familiar with our software and the user interface. But if not, I'm going to give us a quick overview so that nobody feels left behind. Up at the top, we have our top menu, which includes all of the basic interactions with the software. Most commonly, we use it for things like file operations, such as loading, saving, and exporting images. Just below that are the View Controls toolbar. This lets us manipulate how we view the data. We can control the zoom levels, as well as what visualization mode we are in. 2D, 3D, VR, Aivia can do it all. The main area of our software is the image panel. This will display the image data as well as any objects and masks that we create in the image analysis process. Off to the right side, we have several panels. The top one here lets us modify and select different channels in the image, as well as just below that, we have an area to modify and select any objects or object masks that, again, we create in this process. Below that is one we'll be focusing on a lot today. It's our recipe console, and it's where we apply image analysis recipes and select all of the parameters for that process. It also houses a charts tab where we can view information after we've analyzed our images. Last but not least is the contents panel at the very bottom. It has 4 different tabs. The Image Explorer tab allows you to open, view, switch between loaded data sets. Next to that is the Annotation tab, which allows you to annotate, draw, and take measurements of any image data that you have on the screen. Once you have processed and analyzed an image, you may want to edit some of the tracks and masks that you have created. And that tab right here will let you do that. And lastly, we have the spreadsheet. This contains all of the numerical measurements and image data about specific objects in the image. So let's talk about a very common application. Many researchers want to know how many cells are in this image. Well, okay, this one's pretty easy. It's very sparse, it's well defined. You could probably count this just by hand. However, that doesn't scale very well. Images can be much more complex than this. There can be hundreds or thousands, tens of thousands of cells in any given image. Counting by hand is complex, time-consuming, and inexact. But with a software package like Aivia, we can do all of that much quicker, much more accurately, and add in complex measurements on top of all of that. So how do you get from here to here in Aivia? We use a process we like to call a recipe. A recipe in Aivia is just a series of individual image analysis computations that's done in a sequence to get a very specific type of result. Our recipe console here has several main areas. Up at the top, we have one for selecting, loading, editing, deleting, and saving custom recipes. Just below that, we have an input and output section for our recipe. The input channel here, we only are working with a single channel today, but would allow you to switch between different channels on a single image. And below that is a count mask. That's our output. Now, you may be wondering, what is a mask? Don't worry, it's an important concept, but we'll get to it in a minute. Below that are the recipe parameters. These have been grouped into very helpful presets. And lastly, at the bottom, we have an area to preview and apply the recipe. So let's talk about some of these detection parameters. The detection preset helps us segment the image. So up here, remember this? Segmenting is the process of detecting the correct areas of the image. In cell counting, our two most important aspects that we're going to be looking at are the correct segmentation and partitioning of the image. So as I mentioned, segmentation is how well we detect the cells in the image, and partitioning is how well we separate each of those into distinct objects, such as this group down here. The detection parameters there are four main detection parameters. The background removal factor tells the software how aggressively to remove the background noise. The contrast threshold is the minimum amount of contrast needed to detect the edges of the objects. The fill hole size allows the user to specify how many pixels to fill in on the created mask. In a cell, you won't always have an even distribution of fluorescent label, or it could be obscured by a nucleus. For this reason, we've accounted for the ability to fill in this hole in the mask. And lastly, we have a smoothing factor, which removes fluctuations in the perimeter of the cell. Let's take a look at what some of these might look like. Here's what happens when you work with background removal. On the left, we have this image. It's a little bit noisy, and it's got a fairly high level of background information. When you apply a background removal factor, we can remove a lot of that base level noise, and this background is now much closer to a true black. However, we haven't really enhanced the cells in this image. There are a lot of ways to remove background in image analysis. We've used an open residue method, so if you want to look more into that, feel free. But again, this is just an introduction, a practical approach. Contrast threshold is a very important concept as well. And you can see here, I've started with this image with a cell, and I've drawn a line across it. To the right here, you can see the intensity profile of this line. So it starts off in the background. We get the low intensity edge of the cell leading up to this sharp peak, which corresponds to the very bright edge of the cell. And then, of course, it falls off right back down to the background. Adjusting the contrast threshold lets us set a cutoff value for where we want to detect. If we set it low, right here, you're going to see this cell be almost entirely detected. However, if we raise that threshold, only the brightest objects are going to be detected. So adjusting this threshold will help you detect only the brightest objects in your field of view. The smoothing factor is also very important. It tends to lead to more round looking images. You can see here this image on the left has a lot of extra little ins and outs in the perimeter. Once we've applied a smoothing factor, it's a much cleaner edge. So the smoothing factor will help you get more round, clean looking edges on your cells. We also have a subset filtering preset. This lets us choose between what object sizes we'd like to keep once we've actually segmented the image. There are two parameters here. The object size, which is a scale from the minimum size of the object you'd like to keep all the way up to the largest object. And a separation factor that allows the user to determine how aggressively the software will separate objects. Let's take a look at what these do. So in this image, we can see we've segmented some of the image pretty well. However, This object here appears to be just too small to be included. So this image is definitely undersegmented. On the right here, once we've adjusted the object size limit, we can see that this is correctly segmented. Now, the separation factor can be really good or really bad. Down in this area here, we have some regions of the mask that look to be almost touching. However, we can clearly see that those are two separate cells. The separation factor allows us to distinguish between these two cells. But we can't set it too high, or you end up with something on the right. Here we have clearly just one cell, but the separation factor is too high, and it's been partitioned into two different objects. All right, let's go ahead and give you a demo on how this might look in practice. All right, I've already got this cell counting image preloaded. I've adjusted the parameters so it's easy to see. But let's take a look down here at our recipe console. We'll load up the cell count recipe. Our input is only that one channel. Our count, well, this is a great time to talk about our output mask. We'll turn on the preview, and you can see this mask is a green, in this case, semi-transparent overlay that shows us the visual results of our process. This preview will be an important part. We also have individual presets, or individual previews for the separate preset groups. The detection preset will allow us to see how aggressively we want to detect or segment the cells in this image. Low is clearly too low. Medium starts to detect only the brightest segments. So let's work with high. This is different from our total group preview, which allows us to see what this would look like, including the subset filtering. When we look at just the smallest group, we've detected and segmented all of the cells, but we're only interested in keeping these really small ones. We can change this to include a larger group. It's simple to apply this recipe. Once we've selected we want the highest detection and highest subset filtering, we simply click Apply. Here we can see the objects are now correctly segmented and defined by an object bounding box. If we'd like to see how many cells we counted in this process, we can go down to our spreadsheet and click on the Summary tab. Here we've counted 26 cells in this image. Now, we might notice here is where we have that one little cell that didn't quite get detected correctly. To do this, we'll go to our subset filtering and lower this parameter. Here we can preview. We think this will work, but let's take a look at what happens when we get overly aggressive with our separation factor. Just like we see on the image before, when we set this too high, all of a sudden our image is broken into multiple different pieces. So let's just change that back and we'll apply from the beginning. Here we see now our smallest cell is detected. Our separation factor does not cause us to break any cells into different pieces, and everything looks like it has the correct number of cells in the bounding box. We can check this out, go back to our spreadsheet, and this time we have detected 32 cells. All right. Another very common application that scientists and researchers frequently want to use is cell tracking. When you have a time-lapse series of images, it might be helpful to know how those cells move around in space or how they interact with each other. Cell tracking is one way to do that. Now, if we look at our cell tracking recipe, it's actually very, very similar to the cell counting recipe. It's got the same inputs and the same outputs. It even has the same detection preset with the same parameters. However, the subset filtering preset has now been replaced by a tracking preset group. This tracking preset group has 4 different factors to it. We already know about the object size, and we know about the separation factor. So let's talk about the 2 new ones. We have the maximum search range. This is the distance that a cell can move between consecutive frames. So if a cell is very fast moving, or you have a long distance or a long time between individual frames, you might need to increase your maximum search range. However, if your time interval is very low, or your cells are slow or not moving, you can decrease this range. Below that, we have the minimum track length. This is the number of consecutive frames that a cell has to be in the field of view in order to be tracked. So setting this to a very low value means that you will be able to track most of the cells that appear in your image. However, it will take longer. If you set this to a much higher value, it's possible that you can miss some of the cells that you are interested in. We also have the functionality to measure different values about the cells. So on the left here, you can see some of the cells we've looked at before. Once we've processed how they've tracked over time, we can see certain factors in our chart tool. So this is how the cell area of these cells has changed in each frame. Let's take a look at how we would process this in another quick little demo. So here, once again, we've loaded our image. This time we'll select the cell tracking recipe. Our input channel is correctly set to the input channel red here, and we're going to create a new mask for our results. This is where our preview groups become really, really important. We want to see, this is a very similar image. The cells move, but not too fast. So we can preview what the detection group would look like. Once again, low is not enough. Medium is just starting to get there. So we'll stick with high. The tracking group, however, for each frame in this image, we might get a slightly different result. We can't preview all of those results, so we'll go down to this full group preview. We'll want to know what this looks like with a different tracking preset parameter. Low, again, wants to track only these small cells. Medium starts to get there, and high has just about everything we want. This is, once again, a really quick recipe application. Once we've decided on our parameters, we can disable the preview and apply from the beginning. And voila! Here's all of the cells as they move across the screen. To get some of this information that we were just talking about, let's go over to our Charts tab. If we want to know about this group of cells here, we simply highlight them on the screen and they automatically appear in the charts area. We can add certain measurements as well. Once we're in our spreadsheet, we can go over to the measurement tool and select, well, let's take a look. I'm interested in how fast these cells are moving, so let's look at the velocity magnitude. We select that measurement, click Finish, we wait for it to apply, it's very quick, and here it is, right here. Now we can look at this. How did the velocity of all these cells change? Select, there we go. So we can see this cell moves up and down at different speeds, sometimes almost motionless and sometimes moving quite fast between any individual frames. So that's how you would apply a cell tracking recipe in Aivia. All right. Thank you guys so much for tuning in. This has been a very basic introduction to some essential image analysis techniques. We started by looking at who we are as a company. We talked about cell counting as well as cell tracking, and we gave a quick demonstration on how those work in our software, Aivia. If you missed our last episode, it covers some of the basics of how to visualize images in Aivia. This will give you a solid foundation, so I recommend you check that out. If you have any other questions, feel free to reach out to us again on Twitter, LinkedIn, our website with its brand new forum, or in our chat. Quinn, are there any questions?
There are no questions.
All right, excellent. So then, in that case, I would encourage you strongly to tune in next time when we talk about some more advanced analysis techniques. Don't forget to like and subscribe this YouTube video, and we'll see you next time.